This is Official Nerd Business.
Hello nerd boys and girls, welcome back to another Python video. In this video we will be kind of looking at how we can shape up our Euler app as a whole. So instead of all loose files with solution for Euler 1 and Euler 2, we will be looking at making a program that can run any of those files, can share components, can maybe index a couple of things for us, maybe tag some solutions so that we know, hey, this is a problem that uses quadratics, didn't we already do something with quadratics, let's look at the tag quadratics. We will be expanding this a bit. Whenever we come across a simple Python program, I will use the access time to improve on our base application. Everything you'll see here will also be available on my GitHub repository, link in the description. So let's take a dive into it. Here is our the code for our Euler 2 problem. The Euler 2 problem itself was discussed in the previous video, where I said, well, don't mind the if main and the new run function, etc. In fact, if we look at our Euler 1 solution, I have added the run and the text at the top too. We will look at what all of this is in a second. I want to draw special attention now to the fact that I've placed them in a solutions folder. And solutions has an init py with double underscores at the start and at the end. Because of the double underscores, Python has a lot of double underscores, default variables, names and functions incorporated into its language. These are called Dunder functions. Double underscore makes Dunder. So here is init. Basically, because everything is in the same folder, this forms a module, and if there is a special file called __init__py, this will be run whenever this module is included. It will be run at the start to set things up for us, and this is a bit of a complex file, so let's run through this. Most of the magic of everything you see happening is in here. First off, we declare a couple of global variables. These variables are both accessible from outside of the module and from inside it. Keep in mind that we have these global. We will look at what they do a little later on. Then we have an import OS. This one is a standard Python library that uses a lot of that abstracts a lot of operating system operations you can do. So usually when you include OS, you want to access files on the file system, etc. That's exactly what we're going to do here. For every file we find, and we were going to call a module in the directory listing of the directory where this file is in. It's a bit complex here, but os path dir name gives us the name of the directory of the argument, and the argument here is another Dunder file, so that is the literal name of the file that is currently being run, i.e. init py. This gives us a file name, this gives us the accompanying directory name, so that's onbmath/solutions plus a path in front of it, C, code, etc. And this gets every file and every subdirectory in this directory. We're gonna run over each one and call them module while we're at it. So if the file that we're currently looking at is init py, or it doesn't end with py, or it doesn't start with Euler, then we don't want it. We want to continue. We jump to the next item in the enumeration here. If it is something of the form Euler.py, import it. Here is another Dunder, and this is basically the same as this. In Python, before Python 3, this was a language construct that was not mirrored by an actual function in the language. So this was a bit of language magic. But in Python 3 they made the move of everything the language can do, you can do too. So they made a function for it. It's a Dunder function, and this allows us to create a string. Basically just create an argument where you need to have something fixed here. This is a fixed name, it's not a quoted name or anything, it's not a string, it's not a variable, but because we can call the import function with arguments, we can put whatever we want as argument in here. So the file name Euler 001, for example, .py is included here. Solutions dot is added, so the Python package structure needs that dot instead of a slash or anything else. You need a dot, and it is imported. So basically all functions, everything gets imported. We will look at this file gets imported, and it has a run, and it also has a docstring. We will look at why those are standard and what they do in a second as we run through this. In fact, the docstring is coming right up. A docstring in Python is a way of documenting your code. So whenever you have a function and you place three either two double quotes or three single quotes behind it, it creates a docstring, and this string can be as long as you want, and it can hold anything you want. And there's a couple of defaults that you can put in here that describe your function. It is highly recommended that you do comment on most of your code, though I find this a bit excessive for this particular piece of problem of the project. Though I do want to, if you include a docstring at the top of your file, it is taken to be the docstring of the very module itself. So here we have an eval. When you say eval, you just take whatever string comes after it. So we basically we build a piece of Python code on the go, and then it is eval, so it's executed. But this isn't, here we write actual Python, here we just write a string, and it is considered to be Python at runtime. And again, docstring is accessible through a Dunder property in this case. So here the docstring is assigned to S, and we do some formatting on it. We know this docstring has a very particular build-up, a very particular structure, which is noted here. Note that all the Euler files have the same docstring. We have one shorthand title. We have a tab-separated list of inputs. Each input is a semicolon separated triplet of name, description, and type. For example, we want n, the variable n, which is described to be our upper bound, and it is of type integer. Then we have a tab for the next triplet, p, something else, could be a list. As of up to now, we've only seen two problems that require one upper bound n as input, so the fact that you can separate them with tabs is just a nice one at this moment. The next line will have tags. These are tab separated, so you can't put spaces in tags themselves, and you need a hashtag in front of them. That's just for human readability. The hashtag gets stripped later on, and then whatever is left over in the docstring is just put into one final variable. So you could just copy and paste the description from Project Euler in this part, and it's left unaltered by whatever we're doing up here. So here we are processing the docstring. We split it by new line, and we want only 4 pieces. I'm not exactly sure why this argument needs to be one less than that, but it does, so there you have it. So this gives us 4 things. The title is in the first part, if it's present. So this is a bit of a catch. just to see if we did specify a docstring. So we could create an Euler file without the docstring at the top, and this code would not fail because it tests if the split that we did here on the docstring, if it has sufficient elements, and then it puts the element we want in there. Same goes for arguments. Though this is or it could be a collection, and every element in the collection is itself another array, if you will, of 3 elements. We just store them as a whole here, and we will work with them a little later on. Then we do the same for tags. Tags are split off, and let's see, here we see that the tag line is split at the tab, and then we take every string that's in there and we crop off every first character and keep the rest, if once again our safeguard is met, and then everything else is stored into the variable text. Here we have the global description of our modules, which is, if you look closely, a dictionary and not a list. The key for this module is simply the name of the Euler 001, for example, the name of the file. And then we create a tuple in which the first element again is its own name, and then the title, the arguments, the tags, and the text. So now we have a description of our modules stored in this general variable modules. So the docstring for the Euler file, the Euler 1 file itself, is imported into this module, and the docstring is picked apart to see what it looks like on the inside. So we have a title, we have a description of the arguments it needs when you call it to run. We have tags. This one specifically, this one was very basic, so I've simply added the tag basics, and then the description from Euler, project-euler.net, and again the same for our second Euler problem. So that's how we're going to organize our Euler files, but now how do we use them? Well, I have this main file here, and it imports all of the solutions. So because we've set this up to dynamically scan its own directory and add everything to this dictionary here, we can add as many Euler files as we want, and we don't ever need to alter this code again in order to access the new files we've added, as long as we keep the structure up. Then it prints a list of all the modules that it has found, so this accesses so this reads the modules list that we've created. It prints some data about our modules, and we'll see this run in a second. Then it asks the user to type a number. And we'll execute the corresponding script. This pads it out to be a 001 if the user only typed a 1. If we do not know the module, so for instance if we ask for module number 12, well, we haven't solved problem 12 yet, then this will ask the user to try another number and skips back to this part. If we did type in a valid number, it breaks, comes out of this loop. It then selects the module that was entered here, and it will ask us for inputs. So here is the bit about arguments we stored is retrieved here. So that's this in fact the third element of the tuple we create in the init function. 1, 2, 3. So 0, 1, and 2 when you use the accessor on the tuple. It is used here. The tabs are split. Now we know that everything split by tabs is a list of inputs separated by semicolons describing the variable name, description, and a type. We have only seen integer types here yet, so we've only implemented the integer type, but we can extend this a little later on when we need other types as inputs. And the name of the variable is used here, the descriptor part is used here to ask the user for inputs. The input is stored in Q, and Q is then parsed depending on the type that the variable has. And then inst is a list here of instances, so these are instances. Each parameter for the function gets an instance and is placed into this list, and eventually we will call the module in s dot, and s dot is solutions dot. Here goes the script name dot run, and this is the run function that we see here, and run takes 1, 0, 1 or more arguments. Same goes for this run function. And we run it, and this format, as said before, eval is a makes you make Python code at runtime. And we have a string here, and these curly braces are replaced by module. That is what the format string.format function does for us. It looks for each of these placeholders and then fills in that placeholder with whatever argument we supply. So we supply the name of the module, which is inserted here, and then it's run. This is a list, and whenever you use a star in front of a list, it will unpack that list and insert each element that it finds as one of the arguments in the function that we're calling here. So if our list had 7 entries, and the function has less or more than 7 arguments, excluding default arguments, then we would get an error saying that we do not call the function with the correct amount of parameters. But since this only asks for one variable, so one instance is placed here, so we ask this list of 1 to unpack. We will only input one variable here, so this run will just work fine. It runs the function in this bit, it returns a value here, and that value is printed. So that is a lot of talking. Let's see what happens when we run it. Available modules, module 1 and module 2. Please type a number to start. Let's see, number 1. Running below 1000, upper bound 1000. And we get this number. Look familiar? I believe it is. And after this it automatically exits program. And to see that Euler problem 2 works here as well, we type at 2, 4 million, and this is also the correct value. And if, for instance, we would ask for module number 3, which doesn't exist yet, we would get an error. So that's how we are going to build our Euler application. New files will be added here. We'll have a run method, we'll have whatever attempts or subfunctions we need to make it work. And then this main function will simply allow us to enter a 3 and then the parameters needed for 3, and then it'll start to run. And that is for now. Thanks for watching. If you have any questions or anything, please let me know in the comment section. And do mind, you can find everything we've talked about here back on my GitHub, which will be linked in the description. Thanks for watching this video on Official Nerd Business. Don't forget to like and subscribe and click the bell icon. Did we discuss everything you wanted to hear, or did we miss anything? Any topics you want to hear in O&B? Leave your thoughts in the comments. See you next time.